Okay, so apparently we are now live. Welcome to this new session of Coffee Break with Eddyfi. So we are here at home with me to have a coffee. I hope you have your coffee mug. My name is Frederick Reverdy, and today we are going to talk about the basics of total focusing method, TFM. Just a couple of things before we start. There is about a 10-second lag between me talking and you seeing the video and hearing what I'm saying. So bear with me if sometimes I don't see your questions or if there's some weird stuff going on. Also, the video is recorded, so it will be available after on our YouTube webpage. If you are connected right now and not with a Gmail or YouTube, you cannot chat, but if you have one account, just connect and you will be able to put some comment into the chat room. All right, so let's start with the presentation. Okay, as I mentioned, we are going to talk about TFM. Here is my email address, so you can always send me an email after if you have some question. Okay, so we're going to talk about the basics of TFM. I'm going to start with the definition. And first, I want to start by saying TFM is a two-step process. There is a data acquisition part and there is a data reconstruction part. The data acquisition can be done with any type of data acquisition with a phased array probe, but typically most people do it with a full matrix capture or FMC, which I will explain later. Then there is a data reconstruction part, which is basically the TFM. TFM used to be done post-processing, so people were acquiring data on their system, acquiring a huge amount of data, putting the data on their PC, and basically calculating TFM. But recent development in PAUT system, like the Gecko, which was released about 5 years ago, made it possible to do TFM in real time, which is very interesting for inspection on the field. So ASME was revised last year, ASME section 5 in July, to include the full matrix capture and also to include total focusing method. I'm not going to read the definitions here. I'm going to explain them, but you are more than welcome to go and look at the ASME, which describe pretty nicely all the FMC and TFM definitions. So first, let's start with full matrix capture. So again, this is the data acquisition part. This is not the TFM. So FMC can be done with any phased array probe, with or without a wedge. So when I say any, basically you can take any probe off the shelf. You don't need a special probe to do the TFM. You can just use a regular phased array probe. And for the explanation, I'm just going to put a phased array probe with several elements right here in gray on top of a sample that contains two indications. So what we are going to do to do the full matrix capture, we are going to fire the element one by one. So I'm sending a pulse to only the first element. The energy is propagating inside the part, being reflected or diffracted by the indication, and we detect the acoustic energy on all the elements at the same time. And you can see here a matrix with the emitters and the receivers. So we fire the first emitter here, and we receive signals on all the receivers. Then we repeat the process by firing only the second element. Again, we send a nice diversion wave inside the part. We have some reflection from the defect, and we are basically filling another column of our matrix. So element 2, all the receivers. And I guess by now you understand the concept. We fire the element 3. We are filling the column, the third column of our matrix, until we fire the last element of the array to fill the last column of our matrix. So we have fired n times, where n is the number of elements, and we are receiving every single time on all the receivers. So let's say we are using a 16-element probe. We are going to have 16 times 16, 256 signals. Now let's switch to a bigger probe, 32 element. We're going to have 32 times 32, about 1024 signals. And more interestingly, let's use a 64-element probe. You can see it's a big matrix. We have about 4096 signals. So the more elements we use in the probe, the more signals we're going to have, so the more information we're going to have to process later for the TFM. At this point, I want to do a little parenthesis. we are all familiar with PAUT system like 32.128, 64.64, 64.128 systems. The architecture has actually an impact on the productivity of your TFM. If you want to do a 64 element TFM, which I just showed, we're going to have 64 emitters, 64 receivers. Every single time we fire on a 64 element architecture, you're going to receive on a 64 element. If you are only using a 32.128 element, you are only going to fill the first part of the matrix because you only have 32 receivers. So you're going to have to fire a second time all the elements to fill the second part of the matrix. So you're going to decrease your productivity by a factor of 2. So when you are choosing a system, you have to be careful in the architecture of the system if productivity is the most important for you. So that was the FMC, that was the data acquisition. So we have all this information, and now we are going to do the TFM, the total focusing method. And for that, we are going to first define a region of interest, which is here my rectangle composed of pixels. The shape of it can be of any shape, as long as you have a regular grid inside. Then we're going to focus first with only 1 pixel. So we are only looking at 1 pixel of the image. And what we are going to do is we are going to calculate the time of flight for each couple emitter receiver. So each of these signals. So let's pick one of the signals. So this one, for example, which correspond to this emitter and this receiver. So what we are going to do is we are going to calculate the time of flight to go from the emitter to the pixel, from the pixel back to the receiver. So this is pretty easy. This is the sum of the time of flights. So this is basically that represents this time of flight for that particular signal. From there, we are going to extract the amplitude. So we are only going to keep this amplitude for this emitter and receiver. And we obtain 1 amplitude. So let's take one example. Emitter 1, receiver 8. So emitter 1, receiver 8. This is this signal. For this signal, I'm going to calculate the time of flight to go from the emitter 1 to the pixel back to receiver 8. And I extract 1 amplitude. Another example. Emitter 8, receiver 3. So emitter 8, that's the last column, receiver 3. So we're looking at this signal. I'm going to calculate the time of flight to go from this emitter to the receiver. And I'm going to extract an amplitude. And we do that for all the signals. So at the end, we have an amplitude for every single signal. So let's say we go back to our 64 element probe, we have 4096 signals, so we're going to have 4096 amplitudes. And what do we do with those amplitudes? Well, we sum all of them for that particular pixel, and you obtain the amplitude for that pixel. So we have acquired 4096 signals, extracted 4096 amplitude, and now we have 1 pixel. Now we repeat the process for all the pixels of the image. So we're going to basically again calculate all the time of flight for all the signals, extract all the amplitudes. We're going to have a different set of amplitudes. We do the sum, and we have another pixel, and so on. And we basically repeat the process until we have calculated the amplitude for all the pixels of the image. And that's how you obtain your TFM image. So there is a little bit of difference with phased array. In phased array, we calculate delay loss. Here, we basically calculate time of flight and extract amplitudes. So that's the kind of the main difference for the algorithm. But essentially, what we are doing when we are doing a TFM, we are essentially focusing the area at every single pixel of the image. So we are sweeping the beam, focusing the beam at every single image of the pixel. So again, just the animation. So let's stop at that pixel. So for that particular pixel, what the beam is going to do is going to focus the energy right here. So for that pixel, I'm going to have a very small spot, focal spot. So I'm going to have the best spatial resolution for that particular pixel. But we do that for every single pixel. So we obtain the best spatial resolution, obviously depending on the configuration you have chosen. I think by now you kind of get that scanning speed for TFM depends on several factors, but mainly the 3 most important are the number of probe elements. So the more elements, the more data you have in your full matrix capture, so the more data you have to process later for the TFM. obviously the number of pixels. So this is pretty much linear. The more pixels you have, the more calculation you have, so the longer it takes. And also the architecture. It is better to go for architecture that have a bigger first number, so 64, 64, 64, 128, when you want to use a full 64 element TFM probe. For Eddyfi systems, PAUT systems, TFM is available on all the systems. It is available on the Mantis, which is a 1664 system, available on the Gecko, that starts at 32, 128, and it goes all the way to 64, 128. And you can also do a TFM with 128 elements. And you can also use it on our Panther, which is a more desktop system. So here you pretty much don't have a limitation in terms of number of elements, because you can combine up to 16 systems, so you can have a 2000 element if you want. A lot of time I have a question, we get a question about calibration for TFM. What are the necessary steps to calibrate TFM? Well, they are pretty much the same as PAUT. Remember, like TFM is ultrasonic using a PAUT probe, so you have to go through the same calibration steps. The first one is material calibration, so you have to measure the material velocity of the test piece, because we're going to calculate time of flight, so we need to know the velocity. You have to do an element check. You have to make sure that all your elements are working properly. You have to do a wedge delay calibration if you are using a wedge. You want to make sure that you are taking properly the angle and the height of your wedge when you're calculating your time of flight. You can also do a sensitivity calibration, and I will show you that after. So TCG, if you want to make sure that you have the same amplitude everywhere in your region of interest. And there is one additional calibration step, which is called Amplitude Fidelity. So if you actually go, so what is Amplitude Fidelity? So Amplitude Fidelity is a criterion that defines if you have discretized properly your TFM image. Meaning, are your pixels small enough to be able to capture the peak amplitude, the maximum peak amplitude. So this is, those are 3 TFM images. You can kind of see like a side rail hole right here, but calculated with 3 different pixel sizes: lambda over 20, lambda over 5, and lambda over 3. So lambda over 20 is overkilling, but I wanted to show you the response of the defect, so you can kind of see where the maximum amplitude is. So this peak amplitude. As we increase the size of the pixel, you can see that we have kind of a, like a pixelated image. What we want to make sure is, like, as we increase the size of the pixel, that we are not losing this peak amplitude right here. You can see here when I use lambda over 3, I have big pixels. The maximals are here, they are not here anymore, and maybe the amplitude is not the right amplitude that I have right here. So as define amplitude fidelity, essentially what you have to do is, when you select your pixel size, you have to make sure that you are not losing more than 2 dB compared to the ideal case where you have your peak amplitude. So you have to prove that the choice of your pixel size doesn't lead to more than an amplitude drop of more than 2 dB. Because if that's the case, then you can underestimate the size of a defect, for example, or you can simply miss very small indication because your pixels are too big, so you're going to miss the indication. And there are many ways of measuring the amplitude fidelity. You can use a theoretical value, which depends mainly on the central frequency. You can also do it on a Gecko and Capture. We actually provide that value. And we also provide a different method, which actually takes into account all the parameters of the acquisition, the material property, the wedge, the position of the grid, and so on. And I will give you a demo after that. So I'm just going to go. I'm going to pass on the video. We talk about sensitivity correction, and also I will give you the demo after. Why do we need to do a TCG? Well, again, TFM is just an ultrasonic method, and very much like conventional UT or PAUT. If you want to have the same amplitude for a defect, located anywhere in your region of interest, you have to compensate the amplitude, and you have to do a TCG to make sure that you have the same amplitude at every single pixel. For PAUT, ASME states that all the individual beams, so all the angles for sectoral scan, have to be compensated. For TFM, we don't really have any angles. We have region of interest with columns or vertical lines. So the amplitude calibration, TCG, is going to basically impose that you compensate per column to have the same amplitude for every single pixel along the column. And why do we want to do that? So for example, here we have 3 side-ray holes, and we want the amplitude of these 3 holes to be the same and to be close to 80%, to be at 80%. And we want to have that for any position. So we have it here for this position where you can see we have the same amplitude, or again for this position where we have the same amplitude. Again, this is just to compensate any difference in amplitude and energy. Again, I'm going to pass on the video. I will do a demo after. So let's compare TFM to PAUT. And first, I'm going to compare to linear scanning. So here we have a mockup with side-ray hole to draw the sign of M to M. And I think it's pretty obvious when you compare the 2 images that you have a better spatial resolution here. And why is that? Here we are doing a linear scan using only 8 elements. So we are using an aperture of 8 elements, and we are moving this aperture to do a L0 linear scan. So as we are using 8 elements, we have beam spread. Basically, the beam is we have like a beam spread. And you can see that here I have nice response on my first hole, but the response over there is much larger due to the beam spread. So I have my resolution is not as good. Also, due to that beam spread, the amplitude is much, it's weaker here compared to the first hole. And also because I'm doing a L0, well, the first hole is kind of hiding the second one, which in turn is also hiding the third one, and so on. For TFM, we are using the full 64 elements, and we are focusing the energy at every single pixel. So we are focusing right here on the first hole, but we are also focusing on the last hole. So we pretty much have the same focal spot. So that's why the spatial resolution is about the same here compared to here. Also, for full matrix capture, we fire 1 element at a time. So 1 element is sending, a spherical wave, sending energy in all directions. So there is a way for the energy to go between the holes and to reach that hole at the bottom. Obviously, the energy is a little bit weaker compared to here, but still, that gives us some kind of capability to look at defects that are, located one behind another. Now let's compare to a sectoral scanning, and here I'm going to use the 64 element for the sectoral scan, and I'm going to focus the energy right here at the midsection. Here I have exactly my same TFM, and if you look for that particular position, you can see that we have exactly the same spatial resolution, which is normal because we are using the same aperture, 64 element, and we are focusing exactly at the same location. So in both cases here we have the same resolution. But because we are using a full 64 element, so we have a beam that's going to be like highly focused, but our depth of field is going to be very, very small. So here the response of all these holes is in the near field, so that's why we have this kind of bananas like a response a little bit. And for these holes we are in the far field, so our energy is basically decreases very quickly. So let's try to summarize a little bit in table the advantage and disadvantages of TFM over PAUT. So first, obviously focusing. I mean, the name is total focusing method. So for TFM, we focus everywhere in the area of interest. As for PAUT, a lot of time people don't use focusing, or when they do, they are limited to a focus at a constant depth, at constant sound path, or a projection, so along a line. So the result of that is the spatial resolution for PAUT really depends on your choice of focusing. So if you are focusing in the right area, you're going to have a nice spatial resolution, but outside of this area, your spatial resolution can become average to poor, depending on the application, of course. While for TFM, because we are focusing everywhere, our spatial resolution stays the same. which translates into sensitivity. For TFM, as we focus everywhere, if you look at a crack and you are looking at the tip diffraction, as you are going to focus the energy, you're going to have a very small beam at the tip, and you are going to improve the level, so you are going to improve the sensitivity of the tip diffraction. Here, the sensitivity is really going to depend on the position of your focusing. Sometimes you don't need it, but for tip diffraction, that could be interesting to focus right at the tip. Sensitivity to the incidence. When we do PAUT, we are doing our scan plans, doing sector scan, linear scan, and for the bevel, we are trying as much as possible to be normal to the bevel, to detect the lack of sidewall fusion, for example. So the PAUT is very sensitive to the angle of your beam. If you have too much angle, then most of the energy is now going to go back to the probe. Here with TFM, when we do TFM from a full matrix capture, as we fire all the elements one by one, we send energy everywhere. So we always find a way and get a path to basically be normal to the defect, obviously to a certain extent. Then the dead zone. Dead zone, essentially, that's determined by your aperture and the frequency of the probe. Between the two techniques here, I cannot change the frequency. But again, here for TFM, as I fire only one element, my aperture is quite small, so my dead zone is smaller compared to when I'm doing PAUT, especially like linear scanning. When I do corrosion mapping or composite inspection, I'm going to use an aperture, and I'm going to scan this aperture like this, so the dead zone is going to be bigger than here. Okay, now the disadvantages of FMC and TFM, because it's not all roses. First, the data file size. Typically, when we do PAUT, or let's say we do a cycle scan, we are going to have about like 240, 320 points per A scan, and we have a couple of angles. For well inspection, typically we do like a 35 to 70 degree every 1 degree. For TFM, the size of the file is really going to depend on the number of pixels. The more pixels you're going to have, the bigger the file size for every single position. And on average, I would say it's a little bit bigger compared to PAUT. Then, if you want to record the full matrix capture data, so you remember these 4096 signals, if you want to record all of them as you are scanning, then the size of your file is an order of magnitude larger, because now for every single position, you are talking about recording dozens of megabytes per position. So you can quickly, if you have like a 20-inch pipe, and weld, you can quickly have a file of 20 gigabytes. So that's why most of the time we don't actually record the data. Even if our systems allow it, the Panther actually is doing it pretty quickly. But usually we don't do it. Energy. So when we do PAUT, we have an aperture, we calculate our delay loss, and we fire the energy into the part. We have a nice signal. For TFM, we only fire one element at a time. So one element is not sending a lot of energy. So if you are looking at very thick and attenuative material, that can be problematic sometimes. Even though in reception you are focusing, you can have some difficulties for very thick and attenuative material. But it can be improved using other transmission mode like the plane wave imaging, PWI, and still do TFM. I recommend going to our website on the blog where the plane wave imaging is explained, and in a future coffee break we will also have a coffee break about plane wave imaging. Productivity, we talked a little bit about it. Typically for PAUT, if you do well inspection, two probes with TOFT, you are between 70 to 100 millimeters per second, or even faster if the range is not too long. For corrosion mapping, you can go even much faster because you only have one probe doing L0 inspection, 100 to 250 millimeters per second, or even faster. Scanning speed typically for TFM is slower. It is about 2 times to 3 times slower. I will give you a demo after where we actually reach the 75 millimeters per second. But it can also be improved with the plane wave imaging. So again, in a future blog, we will talk about that. If you go to our website on the blog, you can see like how plane wave imaging can improve productivity. So I just also want to say something about some of the limitation. Again, TFM is ultrasound. So when we have a probe like this, and we define our TFM for the first leg and second leg for weld inspection, when you want to look at this part of the TFM, so this is a very high angle, so it's very hard for the probe to focus the energy, very much like PAUT. You can see for these holes right here, we have a pretty nice energy, high amplitude. The beam is actually like very short, but for this specific hole right here, because we have to steer at very high angle, we lose a lot of energy. So this is why TCG is important, because you want to compensate the energy for this part of the TFM. Also, when you do phased array or TFM, a phased array probe cannot focus farther than the near field limit of the probe, very much like conventionality. So if my probe is that big, I have a fixed near field, which is, I don't know, let's say here, I cannot focus farther. So TFM cannot, this is physical limitation, this is not due to the technique, and TFM has the same limitation. Here is an example. So we have a phased array probe, the limit of our near field is right here. So here I'm not focusing the energy, and you can see how the energy is propagating and focusing, at the limit of the near field. Here I'm telling the system, please focus at 45 millimeter. This is past the near field, and you can see that the beam is still focusing at the limit of the near field. So again, if you want to do TFM, you have to choose carefully your probe. All right, now let's switch to a little demo. All right. Okay, so here I have my gecko. I'm connected to my gecko through the Wi-Fi. I have capture right here, and you have here a camera that shows the sample in the probe. So for my demo, I'm going to use that mockup that has 3 holes. So I'm going to use it for my Amplitude Fidelity and my TCG. I'm going to use a very typical, I'm going to use a very typical 64 element, 5 megahertz, 0.6 millimeter pitch. It's hard. The camera is not focusing very well, but this is a shear 55 wedge. So this is the interface. I have defined my part. You can see here this is only 12.5 millimeter, and that will be for my welded plate that I will show you after. So I have calibrated, I have done my angle and height, so I measured the angle and height. I'm going to go directly into the TFM. So in capture, this is where you calculate the TFM. So with capture, you can calculate TFM for any modes. So you can use a wave, T wave, you can use a direct mode TT, you can calculate the corner modes or self-tandem modes they have been called, or the indirect modes. I'm not going to go into that today. We can do that in a later coffee break with Eddyfi. So right now, I'm just going to use TT on the first leg and on the second leg. So this part of the TFM will be considered the TT. This part of the TFM is considered the 40. In the TFM options, so I'm going to use my full 64 element. We have this option right here, the auto button. I talked before about the Amplitude Fidelity, and this auto button is fixing the size of the pixel to make sure that we are fulfilling the theoretical Amplitude Fidelity. So in theory here, I should have a maximum 1.9 dB. Again, this is a theoretical value, maximum drop, which should respect what ASME is requesting. But we have a grid verification here, so I'm going to go into that. This is the Amplitude Fidelity. So the way we have implemented the Amplitude Fidelity is essentially what ISO standard, which is going to be published later this year, going to be. So we have our holes right here. We are just going to position an area to make sure that we are capturing the amplitude of the 3 holes. You have the echo dynamic right here with 1, 2, 3 amplitudes. I'm going to reset it because I calculated it before. And what the system is going to do, I'm going to click on compute. So the system is going to compute 20 TFM with a very small step of lambda over 20. You see it's moving a little bit the echo. And every single time the system is capturing the amplitude for the 3 holes I have right here. Obviously, you are not limited to 3 holes. You can use more holes if you want. Okay. So at the end, so the system has detected 3 holes, and the maximum amplitude variation that it has measured in this 20 calculation was 0.83 dB, which is less than the 2 dB tolerance required by ASME. If we actually look at the amplitude table, because ASME is actually requiring that you explain the, like how you measure the amplitude fidelity, we have the 20 position right here. We have the amplitude in percentage for each hole, so the first hole, second, and third. And we have calculated here if we have more than 2 dB variation, here more than 2 dB, and here more than 2 dB. And the value you have right here is the maximum of these values. Okay. When ISO is going to be published, they are going to ask for to do it in the middle of the world, to actually do it closer to the edge, and also to do it farther. So you'll be able to do 3 amplitude fidelity calculation this way. So to make sure that anywhere in your TFM area, you are not basically using a pixel too big. All right, now let's go into the amplitude calibration. So the TCG. I'm going to reset it because you see it was already calculated. Okay. You can see as I move closer here that my amplitude is actually quite large on this hole, and as I move farther, the amplitude is decreasing because I'm getting, you can see here I'm getting farther from the hole. My angle is actually increasing a little bit, so that's why I have an amplitude drop. So I need to compensate for it. So the way we are doing our TCG, you click right here. So let's see if I can do it. So essentially you are moving your probe, I'm moving forward slowly because I want to capture the information for every single column of my TFM. So here I probably have about 250 columns because I have about 66,000 pixels. So I need to make sure I'm not having any holes. So you see as I'm moving, I'm basically capturing the information for every single column. I miss a little bit some data. And what I usually do is, because we are using coupling and our wedge is pushing the coupling, I'm usually doing it one way and the other way. So this way I'm getting the maximum amplitude. You see here as I go back, I'm filling some of these holes, some of this position for which I didn't get the data. Right. Okay. When I'm happy with it, I click stop. Next, and I'm going to position 3 boxes around each hole. So what you are seeing right here is the echo dynamic, so the amplitude response of the first hole, and you can see that there is a big variation, 56%, and here I'm at whatever 10%. This is my second hole. This is my third hole. I'm just pressing compute, and now the system is calculating the TCG for the 250 columns and for the 3 depth. And you have all this information right here in the table. That table can be exported into the report. Now, if I click, you see I have my TCG, and as I move my column, you can see that the TCG is actually not the same for every column. And it gets stronger here because I had weaker amplitude. Now, if I go into the acquisition, so this is my acquisition right here. What I have right here is my echo dynamic along Z. So this is, I'm projecting all my maximers along the Z axis. So I'm going to put it at 80%, about 80%. So what I want is, as I move, essentially I want to stay for the 3 holes closer to the 80%. In my TCG I have a plus or minus 5%. But you see as I move, I'm quite happy with my TCG. I don't want to talk too early. But my amplitude is essentially staying closer to my 80%. Okay, so now let's switch to, let's do an acquisition. We have done the TCG, we have done all the steps of the calibration. I'm just going to use my half-inch plate, a little bit of coupling. I'm going to use a string encoder. Oops, if I can actually connect it. coupling. All right, I'm gonna press reset. Let's go right here. You can see the C-scan, and as I move some data, I can go back up right here. I can save the analysis. All right, so this is the analysis right here. So for this particular sample, we have about 3 defects. So there is a lack of salvo fusion right here. I'm just going to add about 6 dB. So you see the lack of salvo fusion right here. Here I have a lack of penetration, and here I have a very weak slag. Okay, I'm going to find it. Okay. I can look at the data. So this is a 3D view. I can export my data. So you see here now I'm exporting all my defects in 3D, in a 3D view. So we actually presented this in an earlier coffee break, the data export. I forgot to mention, I went a little bit too fast, about speed. Up, I'm going to go back right here. Actually, for the configuration I've chosen, so I'm acquiring data every 1 millimeter. My maximum scaling speed is about 75 millimeters per second, which is actually quite fast. I went a little bit too fast when I actually did it. I can do it again. Here I can actually display, you can see here, I can actually display the percentage of miss rate. And when I move, all right, a little bit better this time. You see I actually didn't miss any data. I acquired 100% of my data, so 0% missed. All right. Okay, so this is the end of the coffee break with Eddyfi. So let's go and look at some questions. Okay. Let me see. Oh, I have a question regarding does TFM have an impact on battery life? Actually, it really depends on the architecture and the component you are using. A lot of time for desktop system, we are using graphic cards, GPUs, because like gamers these days, the graphic cards are getting more powerful every year. But the graphic cards are using a lot of energy. So if your choice on your portable system is a graphic card, it might have an impact on the battery life. On the Gecko, we use a different component, so it actually has no impact on the battery life. The new Gecko, you can get pretty much like close to between 5 and 6 hours, depending if you're doing a lot of analysis or not on the equipment. So you can use TFM, full voltage, full PRF, and still get over 5 hours of battery life. Let's see. What's the difference between all your TFM what's the difference between TFM for all our systems? Okay, so I'm just going to go back here a little bit. I explained it a little bit earlier, but so let me switch to the presentation. Again, there's a 10-second lag, sorry. So hopefully it's gonna. Okay, so we have 3 different systems. The Mantis, the first one is a 1664 system, so that's entry level. That's the chip system, like for like well inspection and so on. And we have a version that actually can do TFM with 64 elements. We fire 4 times, if you remember the discussion about the architecture. So for this example I was showing you, you can probably reach something like around 20 millimeters per second. So that's kind of an interesting system if you want to do a little bit of expertise with it. If you want to really go on the field and do like full-on inspection, I would recommend using the Gecko. And the Gecko starts with a 32128 TFM 32 all the way to TFM 128. So you have the option of course with TFM 64. I would recommend using 64 element. Again, depends on on the thickness of your part, but here you have an option between 3 different TFM. And for the Panther, you connect the Panther to the PC, and the GPU of the PC is doing the TFM. You have, again, no limitation. The standard Panther is a full 128 system, full parallel, so you can basically do TFM pretty quickly, save all the data. So it really depends on your application. Okay, a question. Yeah, Santiago, I will basically put my email again. So this is going to be on the first slide. Up here you go. It should appear. You should have my email appear in 10 seconds. Can I talk about equipment compliance with the code? I hope it's going to get a little bit better. If not, if I go Santiago, it's F like Frederick, River D, everything attached, at eddyfi.com. But I will put it as a comment into the chat after. Compliance with the code. So if I go back to the lot of slides, sorry about that. If I go back here, essentially what we have done is we have made sure that capture follows what's being described in ASME, but also what's coming in the future code. And that's why we have all these wizards, calibration wizards, to perform your TFM. So yes, capture is, so the Gecko, Mantis, and Panther are fully compatible with the code. Can I use TFM for more complex inspection? Yes, so when we do use, so if I go back to the Gecko right here, I can calculate TFM for more complex inspection. So when I do define the pipe right here, and I use a wedge that's a COD wedge, actually I use circumferential, I wanted to use, sorry, I wanted to do a longitudinal weld, so we are going to do a longitudinal weld. So we are going to use a COD wedge, so the wedge is going to be curved. So capture is able to take into account the curvature of the wedge and the curvature of the pipe, obviously for PAUT, but also for TFM. So yes, you can actually use TFM without the need of an external software directly. And for dual probes, so yes, if we are doing stainless steel or carbon reinforced alloy like a CRA type material or CAS, we can use also dual linear arrays or dual matrix arrays to do TFM. Santiago, you have a Mantis 1664 with equipment not possible making mapping corrosion with 64 elements. Not sure I understand the question, Santiago. If you are talking about TFM, you can do TFM with 64 elements. I would recommend using a hard wedge because TFM is very sensitive to the height of the wedge. So if you're using water column, it is a little bit more sensitive. But the Mantis 1664 needs to have the TFM 64 to be able to use the full 64 elements. So that's the full Mantis. We have 3 Mantis. We have the entry level. We have a Mantis 1664 TFM 16. We have a Mantis 1664 TFM 64, and that's the one you will need to be able to do the TFM 64. Is it possible, more useful to perform FMC acquisition and TFM during post-analysis in order to save memory? Well, that's a good question. If I go back to my presentation, right here. So, sorry. Okay. So here. So if I use a 64 element probe, I have about 4,096 signals. And for each of these signals, I can have up to 8,000 points. So that means like one frame at the maximum could be between 50 and 60 megabytes. So let's say I'm doing a 20-inch weld and I want to acquire data every 1 millimeter. I'm going to end up with a file that's going to be like in the range of 20 to 40 gigabytes. So yes, I can acquire that file. The Gecko has a hard drive of 256 gigabytes, so you see that you will quickly fill the hard drive. I would say like that would be a little bit difficult to handle. So the way I would do it is more do the TFM without setting the FMC, and when you see a defect, you would be basically you could acquire the FMC around that defect for later post-processing, like with sieve analysis or CIVA, for example. There is another way of minimizing the amount of data. Instead of using FMC, so full matrix capture, is to use a data acquisition that will fire less than 64 times. We have something called plane wave imaging. I won't go too much into detail today. We are planning to do a coffee break later about it. But essentially, instead of firing all the elements one by one, what you are doing is you are firing all the elements, doing a sectoral scan. And the idea, of course, is to have this sectoral scan with a number of angles less than 64 elements. Because when you do that, you obtain a matrix that has less data. So this way, if you try to save your matrix, so we have less angles, we have the same numbers of receivers, but our matrix is much smaller. So as we save the data, for each position, we will have less data. Still, that will be quite big, but it will be more manageable. So on the Gecko today, you have this option, or on the Panther, on all our systems actually, except the Mantis, have this plane wave imaging option. You can go, I will show you our website with the blog. We presented something. So the plane wave imaging, we basically fire a plane wave instead of firing one element at a time. And at the end of the process, because you have fire less times, you have less data. All right. I think there is no more question. Let me go back. I think the plane wave imaging is going to be presented next week, I think, by my colleague Laura, if I'm not mistaken. All right. It seems like we have answered all the questions. Just quickly, I'm just gonna show you the website. And when I talk about the blog, so this is our website. Here you have the blog on the top right. We try to publish a lot of information, weekly information, and you can actually filter by articles and by company. I'm just going to apply to M2M. I like my colleagues from the other brand, but today I'm going to do a little bit of publicity for M2M. And you have the blog about TCG and the one about plane wave imaging. So if you want to have more information about the plane wave imaging, you can go into the blog and you will have more information. Also on the top you have something called Eddyfi Academy. So we are trying to make available for free some courses. And you actually have a course, an introduction to TFM. It's only about 30 minutes. So I would recommend going on the website and just looking at it and giving us your feedback. Even if they are negative, we accept positive criticism. And you also have one about the setup creation in Capture, and you can see we have also training for other systems. Thanks Vanessa for the link for the videos. Again, you can go on YouTube after to watch this presentation, or you can watch any presentation from our colleagues that were done the week before and the following weeks. All right, since there doesn't seem to be more questions, I think we are going to end this coffee break. Thank you again for attending. Thanks for the coffee. And see you next time.